Good morning, everyone. My name is Hieu, and I'm very honored to start our presentation today about the cinema management system developed by Group 2. Our group consists of 5 people: Dinh Nam Khanh, Duc Manh, me, Hieu, Ngoc Duong, and Khong Gia Minh. This is the overview of the presentation. Let's first begin with this introduction. Our system was created to help automate main tasks of a cinema, such as booking ticket, managing seat, and generating performance report. We wanted to solve the problems of manual works, especially in such competitive industry. To build this system, we use Python along with the Tkin, the library for user interface, and MySQL for the database. And here are some key features of our system include. You can see right here. So let's dive in more specifically. I'd like to introduce the database design, which is the core foundation of our system. Our database consists of several key entities that work together to support the main function of the cinema management system. First, we have the genre entity, which stores the different types of movies such as action, comedy, drama, and so on. Each genre has a unique ID and a name. This helps us classify and filter movies easily when users are browsing or making selection. The movie entities is where we manage all the details related to the film. It includes the movie title, its duration, and a reference to its genre. To manage the screening location, we use the cinema room entity. Each room has a unique ID, a room name, and a capacity. This allows the system to keep track of how many people each room can hold and which movie are being shown in which rooms. The screening entity plays a very important role. It records the show times of movie, including the date, time, and the room where the screening takes place. We also have a customer entity, which stores personal information of people who purchase tickets. Each customer has a unique ID along with their name and phone number. This allows system to manage user data securely and efficiently. The ticket entity handles ticket booking and connect each customer to a specific screening and record the seat number they chose. This setup is essential for ensuring that seat reservations are accurate and real-time updates are reflected. Besides this quality in core entity, we also included a few extra features, which is staff and feedback entity. You can see right here. Let's talk about the relationship between the entity in our database. Each genre can have many movies, so we have a one-to-many relationship from genre to movies. A movie can be shown in many different screenings, forming a one-to-many relationship between movie and screening. Each cinema room can host multiple screenings as well. On the customer side, a customer can book many tickets. Each screening can have many tickets sold, forming another one-to-many relationship. For feedback, one customer can give many feedback, and one movie can receive feedback from many customers. Now that we've discussed the entity and their relationship, let's move on to the relational schema and SQL implementation. To begin, we create our database with the following command. They set up a new database where all our tables and data will be stored. Next, I will quickly walk through the table creation process. First, the genre table you can see right here. Ensure each genre name is unique and not null. For clarity and consistency, the movie table stores detail about each film, including duration and genre. Cinema rooms keep track of all screening rooms. Each room has a unique name and a positive capacity value to avoid any logical error. Screening record the show times for the movie is linked to both the movie and the room and uses cascading rules so that if a movie or room is removed, all related screening will be deleted too. For customer, we ensure that each phone number is unique for better identification and communication. Ticket connect customer to a specific screening and store seat number. Foreign key constraint help maintain data consistency and automatically delete related ticket if a customer or screening is removed. In the staff table, we store staff details to support staff management with unique emails. Finally, the feedback table lets customer review movie. It includes a rating from 1 to 5, a comment, and the feedback date. To make sure our database schema works well, we inserted some sample data. For example, in the genre table, we added categories like sci-fi, thriller, and action. Then in the movie table, we inserted some popular titles such as Inception, Parasite, and Avenger Endgame, linked to their respective genre and duration. Here are some comments for the cinema room screening, customer ticket, and feedback tool. After adding the data, we ran simple query to check everything was correctly stored and connected. These steps confirm that our database is fully functional and ready for further development or testing. So, to better understanding how all the tables connect with each other, we use MySQL Workbench to visualize our relational schema. As you can see from the diagram, each table includes its primary key and foreign key, clearly showing how entity like movies, customer, ticket, and screening are related. This visualization helps us confirm the structure, check for missing relationship or constraint, and make it easier to explain the logic behind our system design. To make sure our database is well structured from the beginning, we apply first normal form. This step helps us eliminate redundancy and ensure our data is stored clearly and consistently. There are three main principles we follow in first normal form. First one is atomic attribute. Every field in the table must contain only one piece of information, no grouping or combining value in a single column. Second, we remove repeating group, such as having multiple screening times in one row. And third, we make sure every table has a unique primary key to clearly identify each record. For example, our initial idea had a combined table called movie screening, where one row stored the movie title, genre, and two screening times. That structure violated the first normal form because of both repeating group and non-atomic data. To solve this, we broke it down into three separate tables: a genre table, a movie table, and a screening table. After achieving first normal form, we move on to the next step, second normal form. To satisfy second normal form, a table must not have any particle dependency, meaning that every non-key attribute must depend on the entire primary key, not just part of it. The initial problem is that the customer name depends only on customer ID, not the full primary key, which is customer ID and screening ID. So this violates the second normal form. So to fix it, we split the table into two separate ones, the customer table and the ticket table. You can see right here, and it's a component. The third normal form. To meet third normal form, we must eliminate all transitive dependency, meaning no non-key attribute should depend on another key attribute. We found the initial problem right here is that in a table like movies and genre movies right here contain movie ID, movie title, genre name, duration, minute. The genre name only depends on a non-key attribute, not directly on movie ID. So this violates the third normal form. So the solution is we split the data into two related tables, genre table and movies ID table with the component right here. The inside of this part, splitting entities, the first one is rationale. Splitting entities like movie and screening eliminate data duplication while combining related attributes such as customer name and phone number into a single table, improve data centralization and maintainability. The second one is operational benefit. The normalized schema support efficient join, scalable data insertion, and robust integrity checks, handling thousands of tickets without redundancy. The last one is evident advancement. Modular table reduce duplication, enhance query efficiency, and support complex operations like concurrent booking for surpassing non-normalized design.
I will present about the comparison with bad schema example. We compare our schema to poorly designed alternative to highlight its robustness and advancements. The first example, we have the repeating groups. We have the table of the movie screening. We have the movie title, genre, screening 1, screening 2, and screening 3. This violates the first normal form with repeating groups. This leads to the redundant storage of movie title and genre for each screening. We have some scalability issue by adding the fourth screening requires schema modification every time. And when we have the query complexity, is that the searching for the screenings is inefficient. And our solution is in the movies, we store the movie title and genre ID once. In the screening table, each screening is a row with a movie ID, room ID, screening date, and screening time. We have the fortune key. The fortune key links screening to movies, eliminating redundancy. Second example is a mixed entity. We have the batch schema like the table movie booking. We have the movie title, customer name, and the screening time and ticket price. This violates the second and the third normal form. The customer name and screening time have transitive dependency. Combines movies, customer, and screenings causing the redundancy. Example like the repeating the movie title. The third is like the update the anomalies. With changing a movie's title require updating multiple rows. Besides for this comparison demonstrates our schema superiority. The first one is the modularity. We separate the table to enable the independent scaling and maintenance. The second is the integrity of the foreign keys and constraint to prevent the data inconsistencies. We also have the scalability by normalized structure handles the growing data volumes efficiently. We also have the usability by the simplifying the queries and update it to enhance the application development. Scalability and data integrity. The first one, the 5.1 is the scalability, where the first one is the modular design. We use the independent table like movies or screening to allow targeted scaling. We also have the indexing by the primary key and function key up to optimize the joins and lookup. We also have the expandability by the modus table to support features like loyalty programs. The last one we have also is the operational. We minimize the application supports a high concurrency scenario like tenuous bookings. The data integrity, we have the fortune key by the we have some cascading rules, like the example on the list cascade to maintain the referential integrity. We also have some constraints like check unit or non-null to enforce the ability rule or to prevent duplicates. With the third part, we have in the separation. This table store unique data, avoiding duplication like the movie two titles only stored once. Industry alignment. This design reflects the best practice for cinema management system, where the concurrent operation, the robust foreign key, and constraint to support real-time booking system, ensuring reliable transaction processing under high demand. We also have the analytical capability, table-slide feedback, and enable data insights such as the customer satisfaction trends or campaigns effectiveness critical for strategy decision making. The first part we have is the future proofing, the modular structure and the extensible table position the database to integrate with emerging technologies such as online ticketing platform or mobile application without significant rework. Feature implementation, where the first one is optimized with advanced SQL tool like indexing, index, views, shared storage procedure, triggers. Also have the enhanced performance and insight through efficient queries and automation. The second we have the security measure. We use the role-based access control (RBAC) and the backup and restore processes. We also have the audit logging to track the system activity, performance-based masking to ensure the system efficiency and the real-world demands. We also build on a normalized and scalable cinema DBCC scheme.
Let me begin with how we optimize system performance in cinema management. Most operations are very heavy, like looking up movie, retrieving daily sold time, or verifying customer phone numbers. So we created three strategic indexes on movie title to accelerate text-based movie search, on screening date to speed up filtering for today's schedule, on customer phone number to streamline customer lookup. We run benchmark tests on 1,000 execution and observe 85% faster retrieval of screening date, a similar boost for phone number query. Next, we need to simplify data access for non-technical staff like receptionists or ticket clerk. Writing John heavy SQL in the application layer isn't scalable. So we introduced two custom SQL view, daily screening, John screening, movie genre, and room to provide real-time view of or sold time for the current day. Seat availability subtract the number of sold tickets from room capacity to give like seat availability for each screen. The views add data abstraction layer, turning complex business logic into simply query lines. Select from daily screening or select from seat availability where screening date equal to per date. Handling book is not just about inserting a ticket, it involves validation, conflict detection, capacity checking, and more. Instead of duplicating logic in the app layer, we encapsulate it into two style procedures. The first one, book ticket, check if the seat is already taken or where the room is full. If all checks pass, it proceed with the booking. Otherwise, it resists a precise SQL error like seat already booked or screening full. So ticket, validate if a ticket exists before allowing deletion, prevent silent failures. Even with procedures, some of these rules must be informed reactively and automatically. That's where trigger have we implement prevent double booking, prevent inserting if the city already booked. It even log fail attempt into booking audit, update seat availability, and after delete ticket, log every booking or cancellation into audit trail. Raw data isn't enough. We need insight. So we created two EDF. Occupancy rate returns the percentage of book seat for any screening that help managers spot underperforming or overcrowded sessions. Total revenue by date, calculate total ticket revenue per date. We use a flat ticket price for simplicity. A core design principle, we follow the least privilege. That means users only get access to what they need. We define three roles: admin, full control over operation and audit logs. Ticket clerk limited to booking and customer operation, guest read-only access to public movie data. Implementation permission granted using MySQL grant system. Password SHA2 has inside the user table. We simulate a privilege violation. Ticket clerk trying to update movie info in the system correctly denies the request and log it. For real-world deployment, we suggest replacing SHA2 with proof and adding SAT to defend against brute force and dictionary attacks. We took data safety seriously. Our disaster recovery plan includes daily backup via MySQL dump scheduled using cron at 2 a.m. Restore script tests on the stacking database to validate integrity. To achieve full traceability, we log every booking or cancellation successful and failed. Each log includes type operation, screening ID, seat number, who did it, and timestamp. This log support dispute resolution, who booked what, when, and why. This is analytic, check peak time failure pattern, or suspicious activity. Let me summarize the impact of our text store procedure run in under 5 milliseconds. fast enough for live ticket counter. RBAC info strong separation of duty, EDF, and view to data into inside ready for real-time dashboard. Audit log give a forensic level traceability, but beyond that, we design a system that's scalable, modular enough to go with online booking, QR code, and our mobile app skill. Following industry best practices in RBAC, housing and backup, intensible, ready to integrate analytic, loyalty program, and dynamic pricing. This project doesn't just simulate a similar system, it models a production-ready architect for any real-time transactional system.
Next up, we will beginning with our cinema management system, which we will be featuring all the codes and the images that represent the code and the running of front end. We will include a programming language Python, UI framework Tinker, database MySQL, and additional libraries which we will use in Python. Next up is our MVC, which is model view controller. The model will represent the data, business knowledge, logic, and the rules of application, and it communicates directly with the database. And our view handles everything related to user interface UI, and it displays the data to the model, from the model to the user. And the controller acts as a middleman between view and model to handle in user input. The key tables in MySQL database Cinema DBCC is general, movie, cinema room, screening, customer ticket, cancel ticket, feedback, staff, promotion, and booking update. First off, we will have an efficient database connection management, which we will use throughout the program, which is database connector in DB connector.py. And it uses the get connection to actually create a connection pool and get connection and fallbacks to direct connection if pool is exhausted, and configure auto commit for transaction. And we have a simplified implementation. First, we go to a login and role based access control admin ticket clerk, which we have admin in the picture. We will have administrator and ticket clerk, and we will put input username or password, which represent the administrator or ticket clerk to log in. And in our function login, we have just to get user password and verify the name and the password to get login. And our picture here, which we will have add, edit, delete movies, and manage genre. And in our movie model class, we will have to use connect to the database connector, which we will set in the previous slide. And the add movie, which creates a new movie record, and insert movie data to movie table, return a new movie ID. And for the update movie, we will have the update title, genre, duration for specific movie. For cinema room management, which will have a green screen here and also the information above. And it's for the class cinema room model, and it also uses the database connector. The add room, which we will register a room with a name and seat capacity, and it creates a cinema room in the green screen. And the update room, we will update, modify the room names or seating capacity. So next is schedule movie screening, view occupancy rates. The class screening model, we will also use the database connector, and it also have the add screening, which will create a screen with movie room and date and time, which in the picture here. Screen get seat available, which will check available seats, and also we can calculate remaining seats by subtracting sold tickets from the room capacity. Next is the register match information and search for customers. In the customer model, which is in the right part of the picture, and the purpose of it also use database connector, and it get customer by phone number. We search a phone number in order to get the name matching the phone number. In the right corner, we can see that in a picture. And also it add customer if there are no numbers available, and we will add numbers and then add customer name to insert new customer and values. And for the feedback management, it's for customer to have feedback, and it adds feedback function add feedback to get the store rating and the feedback of the movie, the text, and the time spent next to it. And for the booking tickets for screening, visual seat selection, and cancel ticket, the book ticket is what we will click on the green screen to get the box of screen to get the available seats, and the booking ticket, which we will set the current user for audit login, call store procedure to handle the booking, record the transaction, and commit the transaction. For the function to create the seat layout that we have over here, the visualization, it also clear the previous seat layout and get a list of occupied seats for us. The green, which is the available, and the red is the occupied, and we just need to click and insert to get the placement purchase. The track and manage ticket purchase and cancellation with detailed audit trails And in here, we only have a class ticket audit to get the log audit action, which is record ticket related activities. And what it does is we will log it all cost ticket operation, which is purchase, modification, cancellation, and also record timestamp and provide public audit trial for security and accountability. For the reporting, which we'll see the diagram over here, it records the revenue, occupancy rates, and popular movies for us. The class report model, we can get the daily revenue in order here in the green line, and it calculates the daily revenue, which we can see every day, and our dates is the changing at the left up corner. And it just sum up the ticket price for accurate revenue reporting use database functions for optimization. The visualization of screening occupancy rates. We can have the diagram here. It also use to get report model. The get occupancy rate is just getting rates, calculate the ratio, so seats to total seats, and help optimize here the scheduling and pricings.
Another way to back up the database. In the last part, my members have presented a way to back up in the SQL, and now I will show you another way to back up using the Pythons. It will create a timestamp-based file name and run the MySQL dump to export the database, schema, and data. And finally, it saves the backup to specified directory. You can see the overall file structures. Again here, it had 3 folders: the database, the models, the GUI, and also two files in Python and config.py. And it also pretty easy to set up. Just create the virtual environment, activate the environment, and install the needed libraries, and then initialize the database and run the applications. Sum up the security considerations. We used a role-based access control, which consists of the admin and the ticket collect, and also a password hashing, transaction auditing, and database connection security. And also some for the performance optimizations. We used connection pooling, which set to 20s, indexing frequently query columns, and using SQL views, and finally caching mechanism. All about our Python applications. If you have any questions, comment below.